Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and today's video is on classification and discrimination. It's an introduction to the topic. It's part of the course Analytic Methods for Lawyers, and subsequent videos will address ways of remedying the discrimination that occurs, as well as the costs of doing so. One of the major concerns about machine learning is that it seems to discriminate against disfavored groups. And certainly there have been enough examples of horrifying decisions by machine learning systems, such as labeling dark-skinned people as gorillas because the training material failed to include enough dark-skinned persons to prevent the dark skin feature from too frequently pinging the gorilla neuron of some Softmax layer. And of course, if the targets or the feature estimates are based on human judgment, and the judges happen themselves to be biased, the machine learning system will with great efficiency replicate the biases of the humans. Now, until recently, this problem had mostly been the stuff of fiction. The HAL 9000 computer in the movie 2001 brilliantly figuring out how to perform two seemingly contradictory goals. Or Star Trek's M5 computer mimicking the neuroses of its programmer. But our reliance on computers and algorithms has gotten to the point where the salience of this problem has grown quite large. We have algorithms now that make decisions on issues as important as the length of imprisonment, or the access to credit, or identification for purposes of determining whether that was you at the scene of the crime, admissions to schools, and many other areas. Now, in this video, what I want to focus on is a particularly insidious problem, and it's insidious because it can occur without any misconduct, any racism, any bias, or really any mistakes on the part of the humans creating the algorithm. And the machine learning algorithm itself isn't making mistakes. It's just basically doing what it's been programmed to do. And what I want to show is that sort of discrimination against minorities can occur simply as the result of mathematics. In later essays, I'm going to discuss ways to fix this issue, but the sometimes significant costs those fixes can entail. All right, I want to go through example, and I want to create some synthetic data. I'm going to try and keep this as simple as I can. The first column, first feature, there'll be two features actually, is something measurable like income, in which a high value is better. It doesn't even really have to be a single variable. It could be a lot of variables that have been boiled down to a single value, and actually what I'm saying is very generalizable to multiple variables, but we're just going to keep it simple by having one variable like income in which high value is better. The second column is something we're sensitive about, such as race. Doesn't have to be race. It could be handedness. It could be chocolate versus vanilla preference. Doesn't really matter. For my model, what it needs to be is a binary variable. And I'll designate 0 to refer to the most common value and 1 to refer to the minority value. The third column will be performance on something that we care about. This is what we're trying to predict, like maybe a test or performance in law school or success on the job. And again, I'll refer to it as success, but it doesn't really matter what it is. We're just trying to predict something, a discrete value, and I'm going to label 0 as failure and 1 as success. I'm going to construct my data using something called a copula distribution. And a copula distribution is this really cool thing that helps you create complex interrelated distributions out of simpler distributions. And it's if you want to read the mathematics of it, go look up the entry on Sklar's theorem. Now, what I want here is for income and minority race to be negatively correlated. And I want income and success to be positively correlated. I also want to make it, though, so that mathematically race and success have 0 correlation after income is accounted for. That is, any apparent correlation between race and success isn't due to race per se. It isn't caused by race. It's caused by the correlation between race and income being correlated with success. The technical appendix will discuss how you actually do this, but for now what I want you to observe is that the number here in the second column and, second row and third column is equal to, and that's the, remember that's the race and success intersection, is equal to the product of the value in the first row second column and the first row third column. This is the correlation between income and race and the correlation between income and success. You'll also notice, by the way, that the correlation matrix is symmetric. That always has to be the case. If the correlation between A and B is 0.5, then the correlation between B and A is 0.5. So there is a technical appendix to this paper that discusses why this needs to be the case. Why does this need to be the product of these two things? But for now, just take my word for it. All right, but just to emphasize, we're going to create our data so that after income is accounted for, mathematically, race has zero effect on success, and any apparent correlation between race and success is just due to random draws, and it shouldn't end up being statistically significant. All right, let's evaluate our code here. By the way, we're going to have income be normally distributed. We're going to have 20% minority in this example and a 70% success rate. Later we'll fiddle with some of these numbers and see if it matters. All right, so let's get that running. Yes, there are initialization cells at the, here you can see that here. There are initialization cells at the end of this notebook. This contains some functions, mostly cosmetic stuff. I think it's a little distracting to see it up front, so I put it at the bottom, but we do need to evaluate it before we get going. All right, we're done. And now let's generate 2,500 pieces of training data and 2,500 pieces of test data. And really, the only limit on our ability to create data is how much time we want to spend training and analyzing. But I think that 2,500 is a good compromise of speed and accuracy. All right. Also, I do need to make a note here on nomenclature. The word minority has at least two meanings in contemporary American English. It has a mathematical meaning that's independent of any social context. So if there are 101 Dalmatians but 200 poodles, then Dalmatians are a minority. But in the United States, minority also means being a member of a group that's been particularly prone to hostile discrimination on account of group membership. So usually it might refer to African Americans, Native Americans, Latinos, Asians. It could also refer to other forms of discriminated against minorities, at least historically. So you might have discrimination against women, they might be a minority, or gay people, they might be a minority. But in the United States, the two senses of the word coincide. That is, minorities are almost always the minority, although that need not really be the case. Anyway, I don't want to get in this video or essay to get into the precise meaning of the term minority, and so I'm going to use it to evoke the sense that these are real racial or gender minorities, but mathematically it doesn't really matter. All that matters is that by minority I mean that that group has a lower membership count than the group I'll call the majority. All right, let's just make sure that our little copula worked, and let's look at the income distributions of the population by race. I set it up, remember, so that income and minority membership in race are, let's get the right thing, income, that's the first one, and race are negatively correlated. Yeah. All right, let's actually show it. I guess I just calculated it there. Let's show it. All right, so you can see that the red folks, the minority, have a lower distribution of income than the blue folks, the majority. And there's definitely overlap. You couldn't say that if a person's earning, income of 0.5, that they're conclusively a member of the majority. On the other hand, there is separation, so that if you see a person earning, say, 2, you can be pretty confident at that point that they're a member of the majority. All right, we can also see the correlation between race and success. So here, for the majority, you see that most of them are passing the test, like by, I don't know, whatever that is, 3.5 to 1 ratio, whereas among minorities, a majority of them are failing the test. Okay? So remember, this is not caused by race. We've mathematically prohibited that. Instead, it's simply caused because minorities tend to have lower income, and it's income that has a causal relationship and a correlation to test passage. It's also worthwhile taking a look at the information entropy of the distribution of success among minorities and majorities. That's what this code here is doing. And what we see is that the information entropy is lower among the majority, those are the zeros, and higher among the minorities, those are the ones. This happens because majorities have a success rate that's closer to one of the extreme success rates, like 1, it's closer to 1, whereas minorities are more in the middle, and when things are distributed in the middle, they tend to have high entropy. When things are clumped up and there's a predominant category, things have low information entropy. And just to confirm there's nothing up my sleeve, let me use logistic regression to just see if I look at the income and the race, whether the coefficient in front of the race is statistically significant. It shouldn't be, and it should be small, because remember, with these multivariate regressions, you're trying to account for the effects of the other variables. So let's look at our parameter table and one of our famous pseudo R-squareds, and we see that while race definitely has a positive effect on success, income, there is a coefficient there, it's not 0, but it's not statistically significant. It's not even close to statistically significant. And we can see that our model it's doing okay. A Krag-Euler of 0.3 is saying that your model is accomplishing something, although it's not great. And we should spell pseudo correctly. All right. Now, let's try to build a classifier that predicts success on the test. I'm going to use one of our nicer algorithms, gradient boosted trees. We talked about boosting earlier in the course. We're just going to look at our 2 features, our 1 target. We're going to do our classification, and then we're going to see how our strong classifier performs on data it's never seen before. I'm going to have it compute the probabilities for each of the people in the test set, compare that to the target, and get our usual classifier measurements object. And I've set training progress report to none, so we don't actually have to see anything. That moves a lot faster. In the initialization code, I wrote a little function called CMO stats that takes a classifier measurements object, such as CMO strong overall, and it's going to produce a little graph or some information for us. All right, so we're going to see that overall, the accuracy of the classifier is 77%. Here's our confusion matrix. We've got a false positive rate of 49.8%, which is significant. We got a true positive rate. We're getting most of the people who really are going to be successful of 89, almost 90%. We have another Measure of success, that's the area under the curve. We saw that when we looked at the receiver operating characteristic curve. Close to 1 is good, close to 0 is bad, and so our classifier is doing something. And the positive rate, our classifier is classifying people as positive 77% of the time. That's a little bit higher, remember, than a perfect classifier would do, because the way we've set this up, there are only 70% of people who are successful, plus or minus maybe a point of noise. Oops, went too far. All right, so that's our overall situation. Now what I want to do is I want to look at how does the classifier perform on our different racial groups. So I'll figure out which people in the data set are minorities. I'm going to assume everybody else is a majority. I'm then going to rerun our classifier measurements not on all of the test data, but only on people who are in a minority position. And then I will get the stats for the minorities. So let's do that. All right, we did it. We're going to hold off on presenting the information for just a moment. I'm going to do the exact same thing for the majorities. And now let's build a little data set that shows a comparison of the overall population to the minorities to the majorities when a strong classifier is used. All right, let's take a look at this. This is one of the main results in our video. What we see is, first of all, the classifier isn't performing as well on the minority as it is on the majority. It's due to the higher entropy of success among minorities, the classifier is struggling there. And you can also see that reflected a little bit in the area under the curve statistic, where the minority value is somewhat less than that of the majority. But there are two things that should really stand out to you here. First of all, the positive rate for minorities underestimates, well, it's very low. It's 45%, whereas for majorities, it's 85%. That 45% number is a little bit less than the 46.6% who are really positive in the minority group. But the majority, there are only 74% of them that are actually positive, and yet it's giving them an 85, almost 86% positivity rate. But where the real big difference is look at the false positive rate and the true positive rate among the two groups. The false positive rate are people who are not going to succeed, but we predict that they do. And not too many minorities are in that category. The true positive rate are the people who are going to succeed, and we predict that they do. So there's a lot of people who would succeed who are minorities, about 32%, that our classifier is going to say reject. Indeed, the true positive rate for minorities is lower than the false positive rate, or I'm sorry, it's almost lower, not quite lower. It's close to the false positive rate of majorities. That is, these are people who are not going to succeed, and yet if it's a majority, our classifier is saying they're promising. And of course, for those who truly are promising, our classifier is performing well, capturing 93% of them. And so the difference between these two figures is what gives rise to a lot of claims that machine learning systems are biased against minorities. Imagine that this was an imprisonment decision. There are 63% of white or majority people who our classifier is going to let out of prison if we base decisions on this, even though they are in fact going to be a failure when let out on parole or let out of prison. And by failure, I mean perhaps recidivate. Moreover, there are 32% of people who would not commit a crime if they were let out, we are going to, at some considerable cost, keep in prison for an additional length of time. And that's 32% for the minorities and only 6% for majorities. And so you can certainly see the seeds of a serious and legitimate concern about discrimination by machine learning systems in that context. Doesn't have to be prison, could be access to credit, could be admission to a school, so long as you have that mathematical structure that I set up where race is irrelevant, but it's correlated with something else, and that something else is causative and relevant, then you're going to get the phenomenon that we see illustrated here. But maybe it's the fault of all that fancy machine learning. Maybe if we just went back to simpler tests, simpler methods, we wouldn't see this sort of discrimination. Let's see if that's true. What I'm going to do is I'm going to run a classifier, but I'm going to cripple the classifier by making it a random forest with one tree, which is basically a decision tree. Here's the one tree. I'm going to have it not try to use feature bagging. I'm going to say, look at all the features, and I'm going to set a maximum leaf size so that we get a very shallow decision tree here. So let's run our shallow classifier. We're done. We get the statistics. We look at how it did on minorities. We look at how it did on majorities, and then we make a picture of the results. And here we go. Let's see. Well, the overall accuracy is not quite as high as when we used our fancier method, although actually a shallow little decision tree on data this simple is actually doing pretty well. What we do see is that the accuracy is again lower on the minorities than it is on the majorities. That has to do with entropy. We see that the positive rate is much lower on minorities than it is on majorities. That's telling us that we didn't escape the problem by Ludditism and resorting to old school classifiers, and we see the same problem again in which the false positive rate is lower for minorities than for majorities, so we have undeserving people getting positive benefits more often if they're majority, and we see the true positive rate also being much higher for majorities than minorities. Again, more than half of our deserving minorities are rejected by our classifier, and that is indeed a troubling statistic. So resort to simpler methods didn't really accomplish anything here, and it's not so clear that it's really evil machine learning that's at fault. Well, maybe it's because we took race into account in making our classification, and that does seem a little bothersome because it does create an invitation to discriminate. Doesn't mean that you have to discriminate, but it makes it easier if you know what race people are. So let's now hide race from the classifier. And programmatically, I'm doing that by just saying take the first column of the data here, that's income, and of course we do need that last column, which is success. Same strong method as I used at the outset, and we're going to run that through for the population overall. We'll run it through for minorities, we'll run it through for majorities, and let's see if we could only blind our classifier to race, what would happen. And it didn't fix it. The accuracy is still lower for minorities than majorities. Positive rate still way lower for minorities than majorities. The false positive rate still way lower for minorities than it is for majorities, and the true positive rate still lower for minorities than it is for majorities. And perhaps you can see why this is. If race is irrelevant, then not telling the machine about it doesn't really accomplish anything. So that is, and there's actually a bug in the code there. You may not have noticed it, but I did. All right, fixed, same results. Um, let's see if we can make some progress at resolving the seeming paradox that although there are small differences in accuracy rates, it turns out there are big differences in false positive rates and true positive rates among minorities and majorities. As I say, color blindness doesn't hurt or help when success is also colorblind. So we have a kind of a mystery on our hands. The classifier seems to be insisting on discriminating against minorities, even though it appears to be roughly equally accurate on both groups. So how can this be happening? And to unravel the mystery, I think we want to look at something called the ROC curve. It rests on the classifier actually outputting probabilities for success. Not just success fail, but probabilities. And so as you vary the threshold at which the classifier resolves those probabilities into a classification as successful, different false positive and true positive rates result. When the threshold is low, let's say if the probability is more than 20%, we're going to say that that person's a positive. Then the false positive rates and true positive rates are high, and most people are classified as successful. As the threshold increases, however, the false positive rate and true positive rate starts to decline. Like imagine if the threshold were 70%. Then you would have fewer people, whether they were actually positive or not, classified as positive, because fewer of them would be achieving that probability of success of greater than 70%. So the ROC curve sweeps out a trajectory of false positive rates and true positive rates as one varies that probability threshold. So what I now want to do is to look at the ROC curve for the classifier overall in purple, the classifier is applied to minorities in red, and the classifier is applied to majorities in blue. So let's do this and take a good look. It's going to take a moment to generate that curve because there's actually a lot of data that it's got to be looking at. All right, there we go. So what do we see? We see the blue curve overall generally in between the purple curve, which isn't much different, and the red curve, which is lower. And so this is reflecting the fact that minorities have a slightly lower, the classifier is slightly less successful in classifying minorities. That's why the curve is bowed in a little bit more than with overall and majorities. The curve for the majorities and overall is close because they're mostly majority in our population, and therefore they can't be very different. All right, so what's with the dots? The purple dot is the false positive rate and the true positive rate for the classifier overall when it seeks to maximize the accuracy of its classifications. That threshold, whatever it is, has an impact on the false positive rate and the true positive rate for majorities, and it means that there are going to be more people, or a higher fraction of people in the majority that are above that threshold, and therefore the false positive rate and true positive rate are higher for the majority. For the minority, there are fewer people who are going to meet that threshold. That's basically a consequence of having the incidence for minorities be lower than the incidence for majorities. And so you would expect to see that reflected in the probabilities, and we do. So for the minorities, we have about a 20, I don't know what that is, 26, 27% false positive rate, much lower than for majorities, and a 60-something percent true positive rate, again, considerably lower than it is for majorities or for the population overall. So This is basically telling us our story. Notice that if we set the threshold very low, we might have very similar rates for, I'm sorry, this is setting the threshold very high. If we set the threshold very high, we would have similar false positive and true positive rates for minorities and majorities. Basically, almost nobody would qualify. And if we set the threshold very high, as it would be up here, again, we'd have very little difference because basically everyone, regardless of whether they were actually positive or not, would have enough of a probability of being positive that the classifier would say, okay, we're classifying you as positive. It's only because we're picking a threshold kind of in the middle that there's actually a difference between the performance of the classifier, the false positive rate, true positive rate for majorities than there is for minorities. Okay, so keep these curves in mind. All right, now you'll notice these curves are in 2 dimensions. And there's an old book called Flatland, which I doubt anyone reads anymore. It says a novel basically for mathematicians. And it's kind of about how creatures living in a 2-dimensional world don't understand what's going on in 3 dimensions, even though if you think about what's going on in 3 dimensions, it's actually easy to understand. And I think that's our problem here. We've been living in Flatland. So now what I want to do is I want to sweep out the ROC curve in 3 dimensions. 2 of the dimensions are the same, the false positive rate and the true positive rate. But I also want the threshold to be in the 3rd dimension, and I'll make that the Z vertical direction in our display. Same coloring. I'm going to use purple for the population overall, red for minorities, and blue for majorities. And after fixing a little issue, we're back. Here's all the code you need. I'm sorry, it's pretty gory code. Probably shouldn't have even shown it to you, but that's what you need to generate this picture. And if we wait just a moment, there's our picture. Let's look at this. This might be the key graphic in the whole thing. All right, here's the curve in 3 dimensions. Here's our threshold, here's our false positive rate, here's our true positive rate. And you can see the actual trajectories here in this thick solid lines. You'll also see that I've projected the values here down onto a 2-dimensional plane in which all we have is the false positive rate and the true positive rate. And I think you can see that this picture here, down here, looks really exactly the same as what I got up here. Here it's a little more detailed, but that's because the resolution of the plot is higher. But if we look at where that projection is coming from, we see some big differences. What we also see is I've put a plane at a height of 0.5, which is generally where a classifier will set its threshold. It's going to say, hey, if it's more probable than not that you're positive, I'm going to classify you as positive. And if it's less probable than not that you're positive, I'm going to classify you as negative. So I've put the threshold there. And when we put the threshold here, we can see that that red point is intersecting the 0.5 threshold at a lower false positive and true positive value than it is for either the population as a whole or for the majority group. What I'm now going to do is try to rotate this so you can see this even more plainly. And so what you can see is that really this diagram is now, oops, it got a little smaller, let's make it bigger, is really looking a lot like that diagram we saw earlier. And you can see that if you view it in 2 dimensions, why it's hard to understand why it is that there's such a difference between the false positive, true positive rate for majority and for minorities. But if you look at it back here, you can see it's because the plane at 0.5 is intersecting their trajectories at very different points. It takes a lower threshold before the minorities are getting the same false positive and true positive rates as are the majorities. And in fact, that's going to be one of the keys to understanding how one might go about fixing the discrimination problem, if problem you believe it is. Well, I suspect some of you might be thinking the following. I wonder if this difference is due to the fact that the classifier is a little less accurate. It's performing not as well on the minorities as it is on the majorities. What if we could fix that? Would that result in the optimal false positive, true positive point for minorities starting to head rapidly to be the same as it is for majorities? So let's actually try a little experiment here. What I'm going to do is I am first going to fix a bug in the code from having renamed my variables. But what I'm going to do is I'm going to nudge the false positive rate for minorities up just a little bit. And you can see me doing that right here, where I'm leaving nudge the true positive rate up just a little bit. I'm leaving the false positive rate the same, the threshold the same, but for every false positive value, I'm adding 0.05 to the true positive value. And let's see if that actually accomplishes anything. And the answer is not much. We still have this problem. Notice now that these curves are really over each other. If I rotate our graphic, put it flat on, you can see they are right on top of each other. So I've fixed that problem more or less. Maybe I could have added 0.06, but really the problem still is out there. So the problem is not particularly the fact that the classifier is slightly less accurate on minorities than it is on majorities. There's something else going on. Let's try another experiment. Let's flip the role of minority and majority. So now what I want to do is that I want the minority to be more successful than the majority. So the way I'm going to do that is I'm going to change the correlation between income and success. And I'll also have to change the correlation coefficient between race and success in order to preserve any lack of relationship after income is accounted for between race and success. So you'll notice I've changed this coefficient to a negative 0.7 from what it used to be, and I've changed this coefficient from a negative 0.42 to a positive 0.42. And everything else is the same. I'll generate new training and testing data with my new distribution coming out of the copula. Want to make sure nothing's up my sleeve. Hopefully the coefficient in front of the race value will continue to be small and not statistically significant. Let's actually get the parameter table for that. And look, it's small and the p-value is much higher than 0.05. And so I believe my actual distribution that I've drawn fulfills the theoretical relationship that I was hoping for. We can also look at the entropy among minorities and majorities now. And what we're going to see is a reversal of roles, where the entropy among the minorities is much lower than it was among the majorities. So let's now do the usual thing of running our classifiers and seeing what we find. And I'm going to take a moment here to fix the order of some portions of this notebook. All right, we did the entropy. Let's run our strong classifier, gradient boosted trees, on our new training data, reflecting the fact that now minorities are more successful. Get our stats. And let's now do it on minorities and majorities. Did that, and now let's show you the final results here. So let's see what we got. Now the roles are reversed. Minorities are more, the classifier is more accurate on minorities than it is for majorities, and the false positive rate and the true positive rate are considerably higher for minorities than they are for majorities. The positive rate for minorities is now 97%. Very happy. And it's considerably lower for the majorities. So it's not anything about being a minority per se that is causing the issue here. There's something else going on. Let's do one other thing. Let's see what happens if minorities continue to be more successful. But now success, remember before it was a 0.7 here, success was sort of the common thing. Now let's make it so that success is rare. And I'm going to do the same things. Again, our p-value is above 0.05. Coefficient, it's a little bigger here than I kind of expected, but that can happen as a result of chance. We can make sure, let's look at our entropy again, and now we're back to the situation where the entropy is lower for the majority than for the minority, and I think I can explain why that is. That is because for the majority, since they are less successful, their frequency of success is going to be lower than 0.3. And the closer your value is to either 0 or 1, the easier it is for a classifier to work, and the lower the entropy of the initial distribution. The minorities have a value of over 0.3, maybe it's 0.45 or something, and therefore it's very hard for the classifier to work on scenarios where it's equally probable that you're one thing or the other. Again, let's do all that code where we're going to get the strengths of the various classifiers on various groups, and let's take a look at our results. Okay, now what do we see? We see the classifier doing a little better on the majority because it had an easier time to begin with. But again, we see that minorities are doing better in false positive rate and true positive rate and overall positive rate than are the majorities. And so we've got a scenario in which the classifier is more accurate for the majority, but minorities do better. Let's summarize those results. Okay, I've broken things up into 4 categories. This axis represents the success entropy. Lower means it's more in the middle, like 48%. Lower means it's more towards the extremes, like 4% or 96%, so that it's easier for the classifier to work. Higher means it's more in the middle, like 48% or 52%, and so it's hard for the classifier to succeed. In the columns, I have whether the incidence of success is lower among minorities or whether it's higher among the minorities. So this, for example, would represent a situation where minorities are only 3% successful. Easy to predict, but low success incidence. This would represent a situation like minorities have 98% success. Entropy is low, easy to predict, and their incidence is high. Here we have a setting in which their success entropy is high, like maybe 40%, and that's lower than it is for the majority. And finally, here we have a setting in which the entropy for minorities is high, maybe like 60%, and their incidence is higher than it is for majorities, who might be 40%. So what we see is that in our low success entropy, low incidence setting, the classifier is likely to be more accurate on the minorities, but the false positive rate and true positive rate will be lower for minorities than for majorities. If we have a low entropy setting, but the minority has a higher success incidence, then the minority is going to do better on accuracy, false positive rate, and true positive rate. This is the worst case, and this is the one that we often see, in which the entropy is higher. That is, this might be a setting in which minorities are only successful, say 20% of the time or 10% of the time, and the majority is successful, let's say 40% of the time. In that kind of setting, the accuracy is going to be worse for the minority, the false positive rate will be worse, and the true positive rate will be worse. And by the way, because these are worse, clearly the positive rate, which lies in between them, will be worse as well. Finally, this is the mixed blessing for minorities, in which they have a higher success entropy, meaning they're more towards the middle, but they have a higher incidence. And so if that's the case, the accuracy is going to be less, but the false positive rate and the true positive rate should be more. So what do we conclude on balance? We conclude on balance that algorithmic classification, whether done by machine, classic statistics, or humans, is mathematically prone to discriminate. And one way of thinking about this is, if you demand a high level of probability before someone is deemed positive, and the algorithm is any good, those meeting that criteria will generally be those who have higher incidence, more than those who generally have lower incidence. Doesn't matter why, it's just the case. Some of those deemed positive will be false positives, and some of those deemed positives will be true positives, and hopefully the true positive rate will be higher than the false positive rate. But what this means is that the true positive rate of groups with high incidence will be higher than those with low incidence, and it's likely that the false positive rate of groups with high incidence will likewise be higher than those with low incidence. So if majorities tend to have higher incidence, for whatever reason, than do minorities, they're also likely to have higher false positive and true positive rates. And that's going to be true whether you use a fancy, machine learning algorithm, a crude one, or whether you have a human who unknowingly is trying to behave like a machine. That's an explanation for discrimination. It doesn't make it right. Doesn't mean there can't be many other reasons. But if we can get towards a root cause, we can start to think logically about cures. And once we start thinking about cures, we ought to think about their costs as well. Thank you. There's a technical appendix which I will leave to the eager readers, and there's that code at the bottom that I told you about that is used to initialize the notebook.